Now, in this video, we're going to be looking at some examples of how to rewrite a parametric curve in terms of its arc length. Now, it's worth noting that like many arc length problems, the integration is not necessarily always going to be straightforward. And in most generic examples, if you were to just make up a function on the fly, you would not actually be able to do all the integration in order to actually get a representation of the arc length of t in terms of the arc length in order to do the substitution we're going to need to do. So we're going to do some specific examples where we can do it, and then we'll look at one example where you just can't. All right, so this is our original arc length formula. And in order to do our substitution, we're going to modify this just a little bit. So I'm going to swap out my t variable for some sort of substitution. So we'll call it u, because I don't want to do t in both places. And then I'm going to put t in my exponent, because what I ultimately want is I want a representation for formula for how the arc length changes relative to time. So because that's what I'm going to need in order to do my swap. So let's start with a nice straightforward example of a helix. Helices are always nice because the math usually works out pretty well. So let's just try something straightforward. Cosine t, sine t, and t. So then our derivative is going to be minus sine t, cosine t, and 1. And then we're going to find the magnitude of our derivative. And that's going to be sine squared t plus cosine squared t plus 1, which is just going to be sine squared and cosine squared is 1. And therefore, we're going to end up with square root of 2. So when we do this integral, and we'll start with 0 for our particular example, our arc length is just going to become square root of 2. And when I integrate this and then plug in my limits, I'm just going to end up with 2t. And so this is important because now I just have s is 2t, which therefore is going to imply that t is equal to s over 2. And so now I can rewrite my equation as a function of s by simply everywhere, sorry, this should be square root of 2. I don't know why I dropped it, but I did. So everywhere there's a t, I'm simply going to replace t with this expression for t in terms of s. And so now I have my helix expressed in terms of a constantly changing arc length, not necessarily in terms of time, but a constantly changing arc length. So each unit is going to be 1 unit of arc length. Okay, so for the helix, that's not a big deal. Let's try something a little bit messier, but I think is still solvable. And that's going to be t squared and t cubed in either order, doesn't really matter. This is either a 3/2 power, this is either an x to the 2/3 power or a y to the x to the 2/3 power. But it's some kind of 2/3 power function, which is fine. Because it turns out this is actually what's going to make the math work out. So I'm going to take in this, and I can put a constant here in the other direction, it doesn't matter. So what I'm going to do is I'm going to take my derivative. And I can change the coefficients on this. That's not going to be a problem. I'm going to get 2t and 3t squared. And that should be a comma. And then the magnitude of that is going to be the square root of 2t quantity squared is 4t squared, and 3t squared quantity squared is going to be 9t to the fourth. And I can take a t squared out. And then if I take the square root of the t squared and bring it out front, then I will get 4 plus 9t squared, like so. And now I'm going to integrate. I'm going to borrow this. I'm going to integrate my arc length in my dummy variable. And I can do this again with substitution. U is going to be 4 plus 9. I guess I can't use U. We'll do W. 9U squared. And then dW is going to be 18 U du, which is going to give me 1/18 dW is going to be equal to U du. And so my integral, and I'm going to leave out the limits for the time being, 1/18 W to the 1/2 dW is going to be 1/18 times, that's going to be 3/2 power, so this will be times 2/3 U, or W rather, to the 3/2 power. Let's try again. There we go. And then if I put my U back, let's see what I can cancel. 2 can cancel with the 18. That'll give me 9. 9 times 3 is 27. My U was 4 plus 9, my W rather, 4 plus 9U squared to the 3/2 power. And then in terms of my original dummy variable, I'm going to substitute 0 and t. which is going to give me 1/27. Plugging in t is going to give me 4 plus 9t squared to the 3/2. And then when I plug in 0, I'm going to get -4. Now, all of that is equal to s. So now the challenge that we have is we now have to solve for t in terms of s. So let's see, I multiplied by 27, I get 27s is equal to 4 plus 9t squared to the 3/2 minus 4. And so then I get 27s minus 4 is equal to 4 plus 9t squared to the 3/2. And then I take my 27s minus 4 to the 2/3 in order to get 4 plus 9t squared. And then I take my 4 over this crazy thing. Minus 4 is equal to 9t squared. And then I divide everything by 9. And then I solve for t. So then t is going to be, let's see, the square root of this thing. And then the 1/9 I can write as the square root of 9 is 3. So 1/3 out front. And technically this is a plus and minus. So I'm going to restrict the domain to t positive. Although I could do the other side, I could do t negative instead, but I'm going to have to pick the portion of the graph that I'm going to account for with this substitution. And then I can go back to my original equation, which was up here. And now if I want to turn this into r of s, then in the first component, I'm going to take this whole thing and square it, which is going to make this crazy expression. But in this component, I'm going to need to take this and cube it. And I can't really do a lot of simplifying with that, other than saying that this is going to be let's see, I can put this thing to the 3/2 power, and then I can just take the thing under the radical. And then 3 cubed is also going to be 27. So this would be my original, again, some kind of 2/3 power function with solving for the arc length parameter. And see, the thing is, this is solvable and it's still insanely ugly. Now, there are some formulas for like the the unit tangent vector and the curvature that depend on being able to solve for a curve in terms of its arc length. And then things are, if the function is easy, like we saw in the helix, then finding those things actually is easier if you have the parameter already in terms of the arc length. However, taking derivatives of this thing is not going to be a picnic. Even though we were able to do it, it's still not great. Now, that is not to say that we can always do it. So let's look at one last example where we're really just not going to be able to come up with a nice closed form expression for our parameter, and we're just not going to be able to make the conversion. So, for example, if I had some kind of e in my function. Now, if I have some kind of t and t squared, I may be able to do that integration by itself with like trig substitution or something. Not a picnic, but potentially doable. But I throw an e in there, and then I try to take the arc length of this, and it's not going to be a picnic. And there's just not going to be anything that I can really do in terms of finding the parameter, because the thing I'm going to be ending up integrating is just not going to be integrable. So I'm going to end up with e to the 2t plus 1 plus t squared. Now, I do not know how to integrate that. And I don't think anybody knows how to integrate that, like again, with a closed form solution. So there, again, this procedure for rewriting a function in terms of its arc length is doable in a very small number of circumstances. But in some cases, the best that you can really do is to come up with essentially an expression for s in terms of an integral, an accumulation function, basically. And then if you don't mind working with accumulation functions, then great. But otherwise, you just, well, even then, you kind of end up with a mess. So that's really, this is a mess. This is sort of beyond the pale. So again, in textbook problems, they'll usually have you do something that you can do something with algebraically, and they won't generally ask you to do the conversion in situations where you actually can't do the math. Because it's not, you can't just it's not like an arc length where you can just integrate, because the upper limit is not a numerical value. So you can't do a numerical approximation to this. All you can really do is, the best that you could manage maybe is to come up with an accumulation function. And then you would have a hard time then trying to solve for s in terms of t, because t is inside the limit of your integral. And so textbooks usually won't ask you to do those problems. Although that's not to say that professors don't occasionally screw up and ask them anyway.